Tilburg University and MindLabs present TAISIG Talks, the podcast that keeps you updated on the latest developments in the field of artificial intelligence in just 1 hour.
Hello, my name is Pieter Spronck. I'm a professor of computer science at Tilburg University. This is the 26th edition of TAISIG Talks, in which I will discuss AI in healthcare with Görkem and Saygili and Martijn van Leeuwen. And to open, I would like these two to introduce themselves. Görkem, you start.
Thank you very much, Peter. I'm Görkem Saygili. I'm an assistant professor in cognitive science and artificial intelligence department at Tilburg University. I'm doing research on healthcare and I'm using deep neural network architectures in my research.
Martijn.
Hello, my name is Martijn van Leeuwen. I'm a PhD candidate here at Tilburg University, also in the Department of Cognitive Science and Artificial Intelligence. And I work closely with Elisabeth Tweesteden Hospital in Tilburg to do my research, also involving deep neural nets.
Okay, well, you both already mentioned deep neural nets. I should probably remark at the start here that if you talk about artificial intelligence in healthcare, there are many topics that you can touch upon. So we will limit it today, and I'm sure that in future editions of TAISIG Talks, we will get back to AI in healthcare with other people. But these two here are specialists on the use of deep neural networks to analyze medical images. And we have covered deep neural networks in previous editions of the TAISIG Talks several times. Maybe for those who listen to this for the first time, we should quickly say something about what deep neural networks are and why you would use them in medical image analysis. Can I ask one of you to answer this, and the other one can append the answer?
Of course. Well, deep neural networks, in fact, performance-wise, are quite good compared to conventional machine learning algorithms. To understand what deep neural network does, maybe I can give an example. So let's assume that we have a very simple task of classifying cats and dogs images. Or maybe in healthcare to classify whether a tumor is malignant or benign. So it's a classification task. It's a binary classification task. And if, for example, I ask somebody what features to be extracted to do this with sufficient quality, the answer is tough. For example, should we extract like histogram of oriented gradients or scale invariant feature transform or maybe some other kind of features? So it's not an easy question to be answered. Why do we use deep neural networks? First of all, besides, of course, its performance, it also gives us the efficiency that we don't have to think about extracting features from the image data, because with this, for example, if we consider CNNs, convolutional neural networks, with its convolutional layers, it can extract these features for us that are task specific. So at the end, these features are related to the task they're very useful to make the classification. So that's also, one of the reasons, maybe one of the main reasons why we use deep neural networks in this healthcare, in healthcare domain.
Something you want to add to that?
No, not really. I think he summarized it pretty nicely. One thing is, you need a lot of data for training deep neural networks. And in the healthcare domain, there is a lot of data available. But also the type of diseases that are being handled have specific features. And using like these deep neural networks can help with extracting very complex features that are otherwise difficult to manually describe, especially in images, where we also focus on during our research.
Yeah, I can imagine that because if you think about, let's say, 20 years ago, I assume that these these images, they were analyzed by healthcare specialists who knew something about the domain, so they can rate tumors, whether or not they are malignant or not. But I assume there are also other techniques that have been used in the past to try to do this. So, and you mentioned performance of deep neural networks. Are you talking about the quality of what the neural networks do?
Yeah, I mentioned. I definitely mean about the quality. I mean, in the sense that, for example, we use measures for the quality, right? For example, like accuracy or F1 score, or other scores as well, sensitivity, specificity, and so on and so forth. So in terms of these scores, of course, deep neural network architectures have proven their power in the sense that they provide good results.
Okay, but the deep neural networks, as I understand it, so what is the reason to use them is that you want to get an idea of the features on the base of which you can classify images, right? And deep neural networks detect those features themselves, so you don't have to tell them this is what you should find in an image. No, that will find it themselves. So then two things that I want to know about that. So one is maybe the most important one is are these neural networks so strong in this that they can find the same features as humans can?
That is a tough one because, first of all, that we have to understand human vision system to answer that question. In the sense that if you look at for example, like occipital part of our brains, which is the rear side of our skull, we have the region that is specifically there for vision tasks. And if you look at the layers in there, we have V1 cortex, V2 cortex, V4 cortex, anterior, inferior, posterior, and AIT and PIT cortexes, and so on and so forth. So this layered structure, in fact, resembles a deep neural network architecture as well, because we have the same, and that's why we told as deep, because we have these layers, and as we have many layers, it becomes deeper and deeper. So, but regarding to the features, these in V1 cortex, we can think of it as it extracts edges, simple edges, and in V2 it gets more complex and becomes like shapes. And in anterior inferior temporal and posterior inferior temporal cortex, we have object recognition starts to happen. So in that regard, the abstraction level, I would say, for a convolutional network also increases as we go deeper through the layers. So in that regard, it resembles what our brains do, in a sense. Of course, sometimes people call them as black boxes, so we don't, for some architectures especially, we don't know what kind of features it extracts because it's sort of like a black box. But at the end, I would say that, especially for the CNNs, it's sort of similar at the end.
Okay, so is that the reason that deep neural networks tend to work that well? That they are similar to our brains, or at least the visual recognition of our brains?
I cannot give you a specific answer on that, to be honest, especially with the models that we work with are like models that if you have an image, they point out to what pixels belong to a certain region of interest. So that's very straightforward what the model will see. It either sees the thing that you're trying to segment or it doesn't see it. But what features it uses to make that segmentation, those are very abstract and not easy to interpret. You have different kind of models which are more classification based. And there are tools that can help with determining what your model is looking at. The specific names of those techniques, I cannot.
It's not important.
Are not very important.
If people understand that, they have to do some research probably.
But if you look at the first convolutional layers, you will see that the edge-like features are extracted, and if you go deeper into the layers, then you will see the abstraction level increases. So, for human vision, I think it's not possible to understand what kind of information is there in the deepest layers.
So the second question I was interested in is, but actually you already half answered that, is if these neural networks work so well, because you say, okay, look, we have our data set. Data set is labeled, so we can train the neural network on data set. We don't know what the features are, but the neural network learns those features itself. So what then is the research that you're doing? It's not that you take a neural network from the cupboard and say, I train it and it's done. So where is the research going into?
There are a lot of different models that you can try out, of course. And also how you set up an experiment to train such a model is, influenced by so many things, as in how you define your model, how you shape your input. Also, the quality of the annotations are also very important. But there are a lot of things to consider to get a good, nicely working model. You have to follow a couple of steps that your model cannot see the data on which you evaluate it eventually. Otherwise, you can get a very nice model, but the results might be a bit troubled. And if you don't do the research properly, then you might get those results that, we have a very good model, but at the end, it's not performing good on data that it has not seen before. So there are a couple of steps of how to design your research in such a way that it can give fair results, but on the other hand, also give good results. That's a bit of that's most of the research. Most of the time goes into that.
So, and how specific is this? I mean, I know that I was involved with a PhD thesis, at least I had to read it and grade it, that was about just recognizing with a neural network one crack in one particular bone in the body. That was it. And that was 4 years of research to do that well. It was very, very good research, I say. That was one of the better theses that I ever read, but it was very meticulous. But that sounded like, okay, this is so incredibly small, this topic that you're now talking about. If everything that can be wrong with a human body, if you want to build neural networks for that, then how many do you have to do? So how specific is it what we can do and what you are doing?
So what we are doing with the ETZ Hospital is a project is multiple myeloma lesion segmentation. We are building, and Martijn is working on particularly on this topic, and he's using, for example, UNets, which has proven their performance. Have proven their performance on segmentation tasks. And
with segmentation task, you mean?
Multiple myeloma lesion segmentation. So it segments the lesions.
So it is recognizing particular segments of the lesion. Okay, that's a segmentation task.
Segmentation task of the lesions, because lesions are there. We can visually see them. I mean, experts especially can visually see them, radiologists. And we can use an architecture that's so-called UNets to segment those. And there are also different architectures, of course, to be used in this particular task as well.
Sure, but if you talk about, you work on lesions, you train a neural network, a lot of research in that. What can that neural network then do? And how many other neural networks would you need to build, for instance, because this might be a specific type of lesion or a specific type of machine? So how general is it what you do?
Well, the
and what can be done?
Yeah, so the research that we focus on is a disease that results in lesions in bone tissue, and those bones can be spread out through most of the bones actually in the patients. So that model should be able to recognize all different types of regions in a skeleton. So it will not focus just on one particular small bone, but it should generalize well on the entire body. Not all models are trained that way. This is very specific to our project. I think lung nodule segmentation, which are tumors within lung tissue, the very specific region. Those are focused mostly on the lungs, but they should also be able to focus or to find lesions on different locations in the lungs. But depending on what the pathology is that you're trying to identify or localize or segment, you should focus on the region where those lesions occur. For us, that's the skeleton, and other tasks is like a wrist bone, and others are lungs. So there are different different applications and different regions that you should focus on.
And because now you talk about lesions, those are, I think, relatively common. It probably is a lot of data on that. But of course, when you're in hospitals, they also have lots of things where there's not a lot of data available because it's much rarer. So to what extent would it be possible to recognize these kind of things as well? Can you train something for that? Or are you really dependent on having enough labeled data to do something like this? You mentioned at the start that data was very important here, and the labeling of data is, I assume, also very important.
Yeah, well, we have, so the lesions that we find are found in bone tissue, and we have a lot of annotated lesions in bone tissue, but we went over it a couple of times to see whether those annotations were correctly done. And in those corrections, we found that some of the lesions were not really lesions, but that were just bone tissue that was annotated by a radiologist. So the radiologist made a mistake in annotating them, and that also shows how susceptible people even are to making this mistake. So you need to have a very well-defined model to be able to say whether something is a lesion, yes or no. So you really need high-quality annotated data.
Yeah, because I can imagine the following, and you might have to correct me or might have to say how you deal with that, is that if you have, let's say, incorrectly labeled data, not that much. I mean, a real-life expert will not be confused by that because they get a new image and they analyze that image, and that the fact that there is somewhere an image that was incorrectly labeled, that doesn't bother them because they don't use these older images. But a neural network, once that's trained with incorrectly labeled data, that incorrectly labeled data is part now of the training of the network, is in there somewhere, and you cannot get rid of it that easily.
Yeah.
Is that correct?
Yes, inter-observer agreement is an important concern, definitely. Yes, I don't know what is the percentage of the agreement that we have for our data set, but of course we encounter perhaps some
discussion.
Yeah. But at the end, I mean, of course, these are supervised learners. We need labels, and labels are generally assumed to be ground truth. Basically, we assume that they are correct. But if they're not correct, then it, of course, adds some noise to our algorithm. It depends on the amount of noise at the end. It affects, of course, it might affect the accuracy of the algorithm.
Yeah.
In this case, dice score, of course, for segmentation.
Dice score, but also one of the earlier stages of our research where we made the segmentation model with the originally labeled data showed that the data still contained some mistakes and some lesions were not real lesions or the quality was not that good. And that resulted in a model that made a lot of false positive segmentation. So that found a lot of lesions that were actually just regular bone tissue or maybe slightly darker tissue than normal bone tissue. So then we got a model that was able to segment lesions, but was also able to point out a lot of other locations where lesions were supposed to be located, but that was not really the case. So having a good ground truth is really important for this.
And what do you do then?
Go back to the drawing board and look at all of the data.
Yeah, but I can imagine that two things. You can imagine, for instance, that, we see that the neural network indicates things which it thinks are lesions, but when you look at it closer, you say, oh, that's actually not a lesion. So one thing that you could do is say, okay, but now that means that we have more labeled data, because now we have a labeling which is incorrect, and we can basically tell the neural network this was incorrect, and might be able to start use that to correct itself. And the other one would be, okay, you go back to the data set and find out, if that is possible, what data it was using to make this incorrect labeling.
What we can do, for example, regarding to the data problem, I mean, there are data sets, but I think the costly thing here is the labeling, because we need an expert to sit in front of a computer and to label these data for us, which is not any easy, trivial task to do, because they need to spend time on it. What we can do for of course, if we have, let's say, our sample space is not that large as we opt for example, what we can do, there are some other techniques that we can use. For example, self-supervised learning can be a good candidate, or using some pre-trained networks, using transfer learning, using data augmentation can be some different techniques as well. But we have some technical solutions to address small data set problem, especially if we have a small training set, for example, that we can produce some technical solutions for that. But data is costly because for supervised algorithms, we need labels, and labels are the costly part of the data.
Yeah. And the thing you mentioned that you have, when the model makes a mistake, that you can use that data as well to retrain it. We did some research on whether we could make use of those samples, so that examples where the model said this is a lesion, but we knew that it wasn't a lesion because we reviewed it with some expert radiologists on this. And we developed a model to be able to predict whether the model was making a mistake, yes or no. Sadly, that results from that were not that good. We trained a classifier to distinguish between false positives and regular bone tissue, but the results from that showed that it was actually pretty difficult for a second classifier to also determine whether something was a lesion or healthy bone tissue. So we're trying to make use of the information that the model gives us, whether it makes a mistake, yes or no. But the right way of incorporating that is still a challenge.
Have you any idea why it didn't work well? Because I know that in certain other applications this is actually used, and you look at the thing that is trained produces output, and then there's another reward network or something after that says, oh yeah, but this is actually a bad output, and that is then used to find the right output. So why doesn't it work in situations like this?
It might,
if you have any idea, of course.
Yeah, I have a little bit of an idea. If you give the model makes a segmentation. In our case, we focus on segmentations, and then the model outputs that segmentation, and you should be able to feed that prediction back into your model. And the current way that loss function or models are trained and the loss functions that are used to optimize this, they don't handle images that don't have a label very nicely. As in, the loss functions are optimized to localize a label in an image. If you don't have a label, which is the case for a patch that or an image that does not have the lesion, then the optimization of that model becomes more difficult. So that's something that we're looking into currently, momentarily, because it is very interesting to loop that information back into the model, but current structures are limited to do so.
Okay. Is there anything else you want to talk to add to this? Because otherwise, I want very interested in more the application of this. Because you say you do this research together with the Elisabeth Tweesteden ziekenhuis here in Tilburg. Tilburg and what other cities, Elisabeth? Because two cities.
Just Tilburg.
Tilburg,
It's just Tilburg. Okay. So they help you with this research. Are they going to use it? Is this something that they want to apply? Are they already applying this kind of stuff?
Well, hopefully one day, right?
Hopefully one day. At this point, no. No, we're still in the development phase of this project. The data curation and annotation ended a couple of years ago, but yeah, we went over another round of annotations. And I need to write my paper, so I have to focus on getting the research done and not necessarily on implementing in the hospital.
No, I understand that, and as part of a university, we generally don't build things that are actually going to be used, but allow other people to build things that are usable. But so I assume that if they are involved, they really want to get something out of it. Is that knowledge, or are they actually looking forward to developing applications based on this?
I think the main goal is definitely building an application out of this, because that's also one of the things that we target while doing this research. For example, like we're working on a paper now to decrease the number of false positives, right, in the segmentation. And the motivation behind this is if we have so many positives, then we will take time of the expert, right? We will be showing positive segmentations of the lesions, then they all check whether they are really lesions, and it's not good for the daily practice because they will be spending so much time. So I think we are at the end goal is, of course, making something that is usable in daily practice, but when will that happen? Or, that's a difficult thing to say.
Also, if we then eventually get to a point where we think that it's good enough, then you still need to have a lot of approvals and a lot of testing and before you can even apply it in a clinical setting.
But I heard that when these kind of applications are built and are used, it's always as an assistant of a human and not as a separate running application that makes a final assessment. Yeah. Is that indeed the case? Is that how you look at it, or?
I think, if I understand you correctly, whether it makes the final assessment. So that's hard to say, because at this point in time, they're all providing a supplementary idea about the case. So at the end, it's the decision of the radiologist to say whether there is.
I assume that stays that way, but I have seen applications, and I don't remember if that was in the medical domain, but it might have been, where it is, okay, we have a neural network, it's trained to do certain things, humans are trained to do certain things, and these don't overlap. So, of course, there are certain things that do overlap, but there's also parts that humans can do that the neural network fails on. And the other hand, there are things that the neural network can do that humans fail on. And together, they are a lot stronger because they cover more.
Yeah, if we can reach that complementary work, that would be great. But at the end, it's about also regulations, right? Because, for example, who to blame if AI makes a mistake? The developers, the users, who to blame? So, if it's not just about blame, of course, but whenever you let AI to give the final decision, then it becomes a big question mark. Who takes the responsibility out of it? And yeah.
Sure. I don't know if that is a topic that we should really say a lot about here, because this is more about the technology. But in the end, probably a human will sign off on anything anyway. On the other hand, if the AI is doing such a great job that the human starts to trust it, then it will sign off without checking, and then you might have an issue. And of course, then you can say, yeah, but then the human is to blame. But the mistake has already been made. Then it's too late. But
and in healthcare, the mistakes are really, really crucial.
Can be really influential. Yeah, I understand that. And but that's not let's say the level where you're currently working. You're currently working on getting the applications created.
Exactly. Yeah.
Who is responsible in the end? Well, that's probably for other people to decide.
Exactly.
So you mentioned transfer learning at some point, and we might want to say something about that, because okay, maybe leave it open, because you mentioned something about CT scans and PET scans to me, but maybe you should explain that. I don't know if you know anything about that, but
Yeah, so the idea behind transfer learning is that you first train a model on a data set that you have, a large data set that does a specific task, whether it segments something that is related to your field or not. That doesn't really matter. Well, it matters to some extent, but the idea is that you train a model on a very large data set so that it can extract features, and then you later on fine-tune that model on your own data. So you retrain it with the things that it has already learned on that larger data set. And that's a very valuable and handy tool to use, especially in the medical domain where you have very limited amounts of labeled data. Yeah.
And what you mentioned to me, you talked about converting CT scans to PET scans. Is that transfer learning, or should we consider that, because what you mentioned is something completely different?
No, that's not transfer learning.
That's not transfer. So transfer learning, as Martijn has already explained, is about carrying the weights from a larger data set to your small data set problem. On the other hand, this converting PET scans or CT scans to PET scans, or vice versa, or some other conversions are also possible. What we do there is we use generative AI, for example, like we can use diffusion models or generative adversarial networks to do that task for us. And it's not transfer learning, but it is, well, maybe, I don't know, but it's something different. It's not transfer learning. Transfer learning is about, you don't have to use generative AI for transfer learning. You can use transfer learning with CNNs and stuff.
I understand it, but it's, let's say, there is a certain similarity there, because from a CT scan you can get certain information, in a PET scan you get the same information, but maybe in a different way.
That's difficult.
That's difficult.
Yeah, okay, you are the expert here, so you tell me. You mentioned this just in between, and
It is very challenging, I believe, of course, we all introduced ourselves. I'm not a medical expert, but what I know about the positron emission tomography PET scans is that we have this radioactive tracer that's that's just in our veins, right? I mean, it's just inserted in our veins, and then it just causes a biochemical reaction, and then whenever we have the CT scan, then we have this very, very bright region where this biochemical reaction happens, and then it gives an indication of what kind of tissue is there, and so on and so forth for the medical experts. And assume that we don't have that biochemical reaction, can we still extract that information somehow in a CT scan that sort of gives us the same, or more or less the same information as this tracer does? I would say, that might not be 100% possible.
It's difficult.
It's difficult.
And we also had conversations with people from the hospital as well, that we had an intern who really dove into this and did her master thesis on this. And she presented her work at some point at the ETZ for the clinical medical physics department. And they at some point just asked, but we really doubt that it's possible to modulate this metabolic activity from a CT scan, because the information is just not there. So, it's very difficult to be able to substantiate whether that's even possible, but you can always try. And that's what we did as well. That's what the intern did. She tried to recreate PET from CT data, but that was a difficult task.
Okay. From your previous remarks, I understood that you already had done that, but evidently this is in a very early research stage.
Yes, it is.
I'll still come back to the transfer learning again, but in a different way, because you say, okay, we have a big data set. We've trained on a very general problem, and then we have a very specific problem, and we want to have that specific problem. We want to have some network that can work on that, but we don't have a lot of data. But since we have that general model already, we can just train part of it. Is this what I'm saying now correct until now?
Yes.
Because you mentioned also something else here that you could do if you are in a situation where there is very little data overall. Can you say something more about that?
When we have very little labeled data, so then the performance that we can have from a supervised machine learning algorithm becomes questionable, because then probably we will have less accuracy because of the lacking data. What we can do, as I mentioned, there are some techniques that we can use, and one can be, for example, we mentioned transfer learning. Transfer learning can be definitely a solution. Perhaps it will help. Data augmentation, increasing data, maybe synthetically as well. So it can be also a solution. And also, we can use self-supervised learning. So there are these different machine learning approaches: supervised, unsupervised. I think you mentioned a bit about reinforcement learning as well, because of reward and penalty. And there is also semi-supervised learning, which is in the middle of supervised and unsupervised. Self-supervised is a bit, it resembles unsupervised. It just sort of converts an unsupervised problem in a supervised manner, sort of.
I think you have to be... I know what supervised and unsupervised is, and I can therefore derive what self-supervised is, but maybe not everybody listening understands this, and I think these are very crucial terms. So maybe you can say something more about it before you continue with the explanation. About
supervised and unsupervised and so on and so forth. So in supervised learning, we have the labels, and as I mentioned, labels are costly because the experts are making them. In unsupervised learning, we don't need the labels for the algorithm. And unsupervised learning algorithms, examples would be clustering and dimensionality reduction algorithms are good examples of unsupervised learning approaches. We have semi-supervised, that is in the middle. So we have, in general, limited labeled data, but also we have quite a large pack of unlabeled data so that we can take advantage of both worlds, in a sense. In self-supervised, we can also extract information. We can extract sort of labels from the data itself. It doesn't necessarily be provided by the expert, but just, from the data itself. For example, we can create missing locations. We can just discard some part of the data, and then network learns to complete that part so that it trains itself over the data without necessarily explicit labels. Then we have nice weights that we learned from this, and then we can, of course, continue. So it becomes like a pre-trained network, and then we can continue training it on our limited labeled data. So that's sort of self-supervised. In a sense, as I said, it just makes an unsupervised learning supervised by just creating these labels itself from the data.
And are you then doing? What is, in the end, what you produce if you use such a self-supervised method?
At the end, the production is again the same as if you have, it's the same as the supervised algorithm. So at the end, you can end up with a segmentation, but with limited data, perhaps a better segmentation.
Okay. And the reason I mentioned this, we were confusing a couple of things, is that you were also talking about synthetic data, which is data that doesn't exist, that is not real data, but works like real data. Can you say more about that?
Synthetic data. So it's a topic from generative AI. And, well, what is synthetic data? For example, like we have a collection of images, and you can synthesize images that doesn't exist in your training set, but you can synthesize them using this generative AI, and you can perhaps, since, for example, like you can synthesize data with some specific objects inside, then you can use also their labels in the synthesized data so that you can use the synthesized data to augment it on top of your training set so that you have more training samples. Together with your real samples, you can use synthesized samples, and then you can train your algorithm, your discriminator network, on top of this combined big training set.
And what does the synthetic data do? Does it expand your data set, or does it replace the data set?
So it doesn't replace, I think both of them can happen. Well, you can use synthetic data to train your network as well. There is no restriction that you cannot do that. But you need to be sure that the quality of your synthesized images are good enough for your discriminator network to be trained sufficiently well on this synthesized data set. How would it affect your discriminator network? In this case, for example, your classifier, it can affect, of course, noise can affect the performance of your classifier that you train on top of these synthetic images. But it still provides some information, and it can improve. If you augment the synthetic data to your data set, to your training set, then it might very well improve the performance of your classifier at the end.
You mentioned that there were also other, at least you mentioned that to me, that there are other reasons why you would want to have synthetic data.
It is, so it's on the data privacy part of it. So, I'm also interested in the legal aspects of generative AI, because recently I also have some education on law. I have my bachelor degree in law. So synthetic data, for example, can be more private. Can be counted as less private compared to the real data itself. So, and rather than, for example, like transmitting the real data, you can also transmit perhaps synthetic data. You can share synthetic data and that's open for research, by the way. In the scope of GDPR, for example, will we still say that synthetic data is private or not? That is something to be discussed. I mean, that's arguable, but at the end, it can be used to ease the sharing of the data for training neural networks.
Yeah, because I can imagine that, especially in the medical world, this is all rather sensitive material.
Indeed. For example, like hospital in general. I mean, the data in the hospital cannot leave the hospital.
No,
I mean, there are
exactly.
yeah.
There's a lot of patient information that is still in a scan. Yeah. So people who publish their data online, they are very careful with that they anonymize the scans and remove the faces and remove all personal information so that cannot be traced back to the original patient.
Exactly.
So, okay. Could you say something, and maybe both of you can comment that on in general, the state of the art? Where is the world today where AI and medical imaging is concerned, and what do we have to look forward to? So, of course, it's very hard to predict the future, but you must have thought about these things. And you chose to do a PhD in this direction. You still have 40 years to go or so with your work. So, what do you think?
Well, I know that there is a lot of worry inside hospitals, especially within radiology, that AI will replace them at some point. I'm less skeptical. I'm a bit skeptical on that, actually. I think there are a lot of helper models that are being created, like detection models or segmentation models. But I think the tasks are very complex that are being targeted for these models. And I'm not really sure whether we will ever come to a point where we have to replace radiologists with AI models. No, but I'm not really aware of all of the recent advancement in AI in hospitals. I mostly focus on my own work. But yeah, what I know about methods that are being used in clinic are Gleamer, for instance, which is, I think, a program that helps with the detection of fractures. Those things are being used and I think are very helpful tools to aid radiologists, but also people from the first aid. I'm not sure how the emergency room. To localize fractures very quickly. So I think there are a lot of tools that are very helpful, which are not necessarily very complicated, but which can do their task very well. But yeah, they, in my opinion, they will stay helper models for a while, and not really something that can replace a radiologist.
Something you want to add to that?
Well, of course, AI field is really big, and it's hard to be aware of every progress in this large field. But regarding to healthcare, I would say one important thing is recently, one very popular topic is explainable AI, because when, for example, experts want to use an AI system, they want to understand why it gives that decision, what's the reason behind it. And I think explainable AI is very important in that regard, and it's very crucial for also the application of the networks that we develop. We need to make them, I think it's better to make them explainable so that radiologists will know what is the reason behind it. Of course, there can be maybe some other ways of doing this as well. One of them is, if we can just let the experts train the decisions of the AI, maybe they will build also a trust, like as if they are training their students or their residents, right? They guide the algorithm, and then they are sure that it makes the right decisions according to their opinion. Then perhaps it intrinsically builds a trust relationship between AI and human beings, so that they will be sort of also maybe complementary as well. It's not our research field, for example, like there is huge progress in large language models and natural language processing tasks. These are also, I would say, very important, very progressing fields in AI, which also can be used in a hospital environment at some point, because, they can also make use of these things, maybe to interfere with the AI algorithm. NLP can be integrated inside these systems to make better communication.
Yeah, because what you now mentioned is all work for AI experts, not for the medical experts, but probably they have a role to play as well there. So there's one final thing that I wanted to bring up, and which is kind of a very different topic, but actually you talked to me about it, and is that you're currently also part of your job is going to change. So maybe you want to say something about that.
Yes, that excites me a lot. We are just opening this new track, cybersecurity and AI, AI and artificial intelligence and cybersecurity, which is a Dutch track. And
so this is for students?
This is, exactly, for master's students. It will be sort of it has this societal focus, but at the end it will be, of course, technical as well. So that's what make it special. So we will have also courses related to regulations and law, but also courses on ethics, and also courses on technical subjects, including deep learning, data science, cybersecurity, and so on and so forth.
Okay, and when is this going to run?
It will start in next academic year, September 2025, and the admissions are open. I don't know if you can put a link under this.
Oh, who knows? But people can find that on Tilburg University website. But I was just thinking that maybe next year we should return to this table and talk about cybersecurity.
That would be great.
Then we have another topic that we should really focus on. Is anything one of you wants to add?
Not really, actually.
If not, then I think we can end it here. Thank you very much.
Thank you very much for
interesting,
inviting.
and there will be more on cybersecurity and on AI in healthcare in the near future.
Great.
Thank you.